So we have 4% of baryonic matter, 26% of dark matter, the actual very, very minor part component, which is radiation, which is around 10 to the minus 5%. And then what is the major component, which is dark energy, which is 70% of component of the universe. We will see, what we see is that the first step of writing some good models is to have a metric. And for obvious reasons, since the gravity is the predominant force on big scale, that acts on big scale, and we are saying that the universe, cosmology, which looks at the universe as a whole, is looking at the big scale of the universe. Of course, the metric and the base of the metric here, and the basis of the metric we are going to use, which means the geometry of space-time itself, is of course that of general relativity, Einstein's general relativity. So we have at first have to be able to define a metric. So what kind of geometry of the space-time we are looking at. So when we define a metric, what we are saying is how you define the distance between 2 points. This is the definition of metric. So 2 points in general relativity are called events. So we have 1 and 2, and we have these 2 events described by the Cartesian coordinates in 4 dimensions, so 3 space dimensions and 1 time dimension, and we will have the 2 events. So we want to have a definition of the distance between these 2 events. This is defined by the following quantity, which is ds square equals g alpha beta dx alpha dx beta, which is equal to g00 dt square plus so what we have here is so this is a time So what we have 3 components. The first term is the time component, the second is the mixed component, and the third is the spatial component. So This here, J alpha beta, is the component of the so-called metric tensor, which is the one that describes the geometry of space-time. So the metric is defined uh, by these components, and as we've seen, uh, they describe different components accordingly to the values they take. So this is the time component, this is the mixed component, and this is the space component. So we see that the distance, the interval between two events in relativity, in theory of relativity, has different definitions. So, with respect to the sign it takes, and describe different kinds of intervals. So, more specifically, we are looking at the sign of the square of the we are looking at the sign of the square of the metric, which can be positive, equals to 0, and negative. So the first one, the positive square of the metric, defines an interval which is called time interval. That equals to 0 defines a light interval, and that negative is the space interval. So when we look at the four-dimensional space-time, the photons move on geodetics that are described by the curves ds equals 0. So these define what's so-called the cone of light, and so we have that an event, or the interval between two events, is inside or outside this cone of light, and if it's exactly equal 0 is specifically on the border of the cone of light, so which is where the photons travel, so that's why it's called light interval, because it's the it's a distance that photons traveled, so at speed of light per definition. So we've seen the general definition of the metric with the three different components: the time component, the mixed component, and the space component. So we can define the 3D spatial metric for a proper time, so at a fixed t, which is dl square equal g j I dx I dx j. And also, we've said that, of course, the theory must be founded on the cosmological principle. So there are no positions or directions privileged. So the mixed spatial time so the mixed time spatial terms must be null. So mixed terms mixed terms equals 0. So this term goes away. This can leave us to write a generic form of the metric, which is in agreement with the cosmological principle, which is ds equal c square dt square minus j minus g j I dx j, which can be written as such. Minus dl square, which is what we've defined as the 3D spatial metric. So this definition here has a different form with respect to different times, with respect to different kind of geometry. So the geometry of the universe. So the first one we see is the Cartesian geometry, flat universe. This describes an Euclidean flat space, flat surface with the curvature radius infinite. So we have an Euclidean flat surface with radius of curvature infinite. So this is better described with polar coordinates. So we have the L square equals the x square plus the y square, which is equal to the rho square plus rho square the phi square, with rho, which is defined between 0 and infinite, and phi, which is defined between 0 and 2 pi. Also, for handiness, we introduce two parameters, which is r, defined as rho divided a, and a A is a dimensionality parameter, which we will define better later. This enables us to write the metric as such. dl square equals a square times dr square plus r square the phi square. So this is the metric for an Euclidean flat surface, so a Cartesian universe. For the second kind of geometry, we have spherical geometry. So a spherical surface with positive curvature, radius of curvature, one over r square. So, of course, this is better described by spherical coordinates, which we remember are theta defined between 0 and 2 pi, phi defined between 0 and 2 pi, and r defined as the radius of the sphere. So we have dl square equal r times sin square theta d phi square plus d theta square. So going back to the parameter we have defined before, a and r, we can write this in a form that is similar to the previous one. So this, what we're doing here is to be able to write the different metrics for the different geometries in a similar form, and we will see why, because we will have at the end a generalized form that depends on a parameter which in itself describes the different geometries and the different kinds of universe. So here we have a square times dr square 1 minus r square plus r square d phi square. So we will see one after the... So we will look at them together and we will see immediately which is the generalized form that described them all. So the last one is a hyperbolic surface with negative radius of curvature. So this is the metric described in hyperbolic coordinates. No, cancelliamo. So this is the metric described using hyperbolic trigonometric function r equal sin h of theta and rho defined between 0 and infinite. And so this writes as previously as dl square equal a square dr square divided 1 plus r square plus r square d phi square. So if we look at them all together, this is the Euclidean flat, this is the spherical, and this is the hyperbolical geometries. We see very clearly that there is a simple way to describe them all with a generalized form of this equation. So if we look at this equation in its form, we see that with different values of k, we can recover the different expressions we have found of the metric for the different geometries of the universe. So, more precisely, we have k equals 1, and this term goes to 0, and so we have the first expression for the flat Euclidean surface. For k, no, go back, fuck you. So for k equals 0, we see that this term here goes to 0, and so this describes the first expression that we've seen for the Euclidean flat surface. For k equal 1, we get the spherical metric, and for k equal minus 1, we get the hyperbolic metric. Also, we can give a definition to this A, which is the expansion factor. A is the expansion factor, which describes the expansion of the universe as a function of time. So if we write the phi in square in 3 dimensions, we have the omega, which is equal to the theta square plus sin square theta, the phi square. And so we substitute this for the phi square, and we get ds square equal c dt square minus a square t times the r square 1 minus k r square plus r square sin square theta the phi square plus the phi square. And this is the so-called Friedmann-Robinson-Walker metric. This here, as we said, is the expansion parameter or expansion factor.